Welcome to the Deep Dive, your shortcut to being well-informed. Today we're focusing on something truly transformative, high-speed rail, HSR. It's, well, arguably the fastest and most efficient ground transport we have.
Yeah, and we've gathered some really fascinating sources today. We're going deep into its definition, its surprisingly long history, how it's spreading globally, and, importantly, how it competes with planes and cars.
Absolutely. So our mission for you is pretty straightforward. We want to unpack what HSR really is. It's more than just a fast train. We'll trace its path from, believe it or not, 19th century ideas right up to today's bullet trains.
And figure out why it's become such a dominant force in that sort of medium-distance travel market across the world.
Okay, let's dive right in, because high-speed rail sounds simple, but the moment you look into it, you find there isn't one single global definition. That really threw me, actually.
It is interesting, isn't it? What jumps out is that the experts, the engineers, they don't just define it by a top speed number. They talk about an integrated system.
An integrated system.
Right. Yeah, it's the whole package, the specialized trains, the way they operate, and this is key, the dedicated tracks built just for them.
Right, the infrastructure. So it's not just a fast train on any old track. But we do need some numbers, surely. What speeds are we talking about according to, say, the International Union of Railways, the UIC, or the EU?
Okay, so they generally use two main benchmarks. For completely new lines, purpose-built, the track needs to be designed for at least 250 kilometers per hour. That's about 155 miles per hour.
Okay, new lines, 250.
Right. But then there are existing lines that get a major upgrade. Think better tracks, safety systems, the works. For those, the threshold is a bit lower, at least 200 kilometers per hour, which is around 125 miles per hour.
That distinction's important, because you do hear about regular trains hitting 200 kilometers sometimes, but they aren't called HSR. So it really comes back to that dedicated infrastructure.
Exactly. The UIC and EU really stress this system mentality, as they call it. A normal train hitting 200 for a short burst. That's one thing. But consistently, safely running at those speeds for hundreds of kilometers. That needs the special signaling, no level crossings, ways to control all the variables. Without that whole system, it's just not HSR in their book.
Got it. So let's zoom in on that 200-kilometer number for upgraded lines. Why that specific speed? Is there some kind of, physics barrier there?
There really is. It's a critical point for engineers because above 200, the technical challenges just ramp up significantly. For instance, the impact of tiny imperfections in the track geometry gets much, much worse.
Geometric defects. What exactly does that mean?
Yes.
Like small bumps or slight curves?
Precisely. Even minuscule flaws in how straight or level the track is, things you wouldn't notice at lower speeds, become major stress points. It affects wear and tear, maintenance, and definitely passenger comfort, and safety, of course.
I bet.
And then there's adhesion. The grip between the wheel and the rail starts to decrease noticeably. Plus, aerodynamic resistance, it goes up exponentially.
Ah, the air resistance. That must be why they have that classic bullet shape, right?
Yeah, that's a huge part of it. Yes, you're basically pushing a massive object through a thick wall of air at high speed. Takes enormous energy. And don't forget tunnels.
Oh, right.
Entering a tunnel at, say, 250 kilometer creates a significant pressure wave, that sonic boom effect. It can be really unpleasant for passengers if the tunnel and train aren't designed to handle it. Plus, it makes it hard for drivers to read traditional trackside signals.
Makes sense.
Okay.
One quick note for our listeners, especially in the U.S., the definition there is actually a bit different, isn't it?
That's right. Federal law in the U.S. sets the bar lower. They define HSR as intercity service expected to reach sustained speeds of at least 110 miles per hour.
Which is only about 180 kilometers per hour.
Exactly. So under the U.S. definition, you might include lines that wouldn't quite meet that international 200-kilometer router threshold for upgraded tracks. It's just a different standard.
Okay, definitions covered. Let's get into the history, because this part is really cool. We think 1960s Japan, maybe, but the dream of really high speeds goes way back. Tell us about that German experiment in 1903.
Oh, it's incredible. A real feat of engineering, way ahead of its time. Basically, starting around 1899, some big German companies like Siemens and AEG worked with the Prussian State Railway. They electrified this military test track near Berlin between Marienfeld and Zossen.
And the results were just mind-blowing for the era.
Yeah.
In 1903, they had these special electric rail cars hitting speeds over 200 kilometers. One reached 206.7, another 210.2.
Over 120 years ago, they proved the basic tech was possible, but Like you said, the question is, if they could do 200 kilometers in 1903, why did it take another 60-plus years for true HSR service to launch?
Yeah, what was the holdup? My guess would be the cost of the track, the infrastructure.
That's exactly it. Building and maintaining tracks smooth and stable enough for those speeds over long distances just wasn't economically viable back then, and maybe the demand wasn't quite there yet, so it stayed mostly a tech demo.
Until the 1930s, maybe, with the streamliners.
Right, that's the next step. You get these famous diesel trains like Germany's Fliegender Hamburger, the Flying Hamburger, hitting 160 kilometers in regular service in 33.
And the U.S. had the Zephyr around the same time.
Yes, pushing speeds up. But the moment that really showed conventional rail could handle extreme speeds, that came after the war, in France.
Ah, the 1955 test. The CC 7107 locomotive breaking 300 kilometer.
Reaching 331 kilometers, yeah, on standard track. But it wasn't just about setting a record. That test revealed a serious problem.
Which was?
Something called hunting oscillation. Basically, at very high speeds, the wheel set started wobbling side to side violently on the track.
Oof, that sounds dangerous. Like the train could literally shake itself off the rails.
It was incredibly dangerous, a near miss. But crucially, they figured out why it happened and how to fix it. That led directly to developing yaw dampers, sort of like shock absorbers for sideways motion, which are now standard on all high-speed trains.
Okay, so France proved it could be done, and done safely. But it was Japan that really put it all together for mass transit, right?
Exactly. The Shinkansen, 1964. This was driven by pure necessity.
How so?
The Tokyo to Osaka corridor was, and still is, incredibly densely populated. Japan needed a way to move huge numbers of people efficiently, especially since they relied heavily on imported oil. Trains were the answer.
And they made that key decision. Build a new line using standard gauge tracks, 1,435 millimeters, not their existing narrow gauge network.
A vital choice for stability at speed. So, the Tokaido Shinkansen opened just in time for the 1964 Tokyo Olympics. Those first Idaho Series trains, they hit 210 kilometers.
Cutting the Tokyo-Osaka trip down to just over 3 hours, and that's where the bullet train name came from, Ding and Reisha.
Yep. But speed was only half the story. The capacity was revolutionary.
Right, the sheer number of people they could move.
Absolutely. Trains with up to 16 carriages, sometimes double-deckers later on. The numbers are staggering. 100 million passengers in just the first 3 years, over 10 billion total since it started. Japan proved HSR wasn't a gimmick. It was essential infrastructure.
A complete game changer. So Japan lays down the blueprint. Who picks it up next? This kicks off the global race, especially in Europe and later massively in Asia.
Europe jumped in fairly quickly. Italy actually got the first European HSR line operational, the Florence-Rome Direttissima, opening in sections from 1977. Designed for 250 kilometers.
Italy first. That's interesting. I always think of France next.
Well, France definitely made the bigger splash globally with the TGV, the train à grande vitesse. The first line, TGV Sud-Est from Paris to Lyon, launched in 1981. Initially 260 kilometers, soon bumped up to 270.
And didn't France make a crucial decision about power early on? They looked at gas turbines.
They did. Early prototypes used gas turbines, but then the 1973 oil crisis hit. Big wake-up call. France pivoted hard towards nuclear power for its electricity grid.
Ah, right.
And they decided the TGV had to be purely electric. It was a strategic masterstroke, really. Tied their flagship transport project directly to their domestic energy policy, making it less vulnerable to oil price shocks. Very smart long-term thinking.
Definitely. And elsewhere in Europe, the networks just kept growing. Spain's a huge example. Started in 92, Madrid-Seville line for the Expo.
And now, Spain has the longest HSR network in Europe. Almost 4,000 kilometers as of 2024. And like Japan, they chose standard gauge for their new high-speed lines, separate from their older, wider Iberian gauge network.
Which probably created some connection headaches initially, but was better for speed.
Yeah.
It also highlights something interesting. HSR lines crossing international borders. That really only happens extensively in continental Europe and parts of Asia.
That's a good point. Integration is still evolving. But if we're talking sheer scale today, one country just dominates the map. China.
Oh, absolutely. The expansion there has been incredible, driven partly by that big economic stimulus after 2008, right?
Massively. China built out its HSR network at a pace nobody thought possible. As of last year, 2023, China has something like over 2/3 of the entire world's high-speed rail track, over 40,000 kilometers.
Just staggering numbers. And they're pushing the speed limits in regular service, too.
Well, the absolute fastest public service is actually the Shanghai Maglev,
Yeah.
using magnetic levitation, not wheels on rails.
Right. The maglev, that's kind of its own category.
It is. Hits 431 kilometers, that's 268 mile per rack, on its short 30-kilometer airport run. But for conventional HSR, the fastest trains currently running day-to-day are in China, the CR400 Fuxing trains, and now also in Indonesia using similar tech. They operate at 350 kilometers.
350, wow. And just for context, the absolute one-off speed records are even higher.
Oh, yeah. For testing, they push the limits. Japan's L0 series maglev test train hit an insane 603 kilometers back in 2015.
603, good grief.
And for conventional wheel-on-rail, the French hold the record. A specially prepared TGV hit 574.8 kilometers in 2007. So the technology can clearly handle immense speeds, even if daily operations are sensibly capped lower for efficiency and wear.
Okay, so the tech is there, the networks are expanding. Let's talk about where HSR really wins the fight against planes and cars. It's not for every journey, right?
No, definitely not transatlantic. HSR finds its sweet spot on journeys that take, let's say, between 1 hour and about 4.5 hours. That usually translates to distances of maybe 150 up to 900 kilometers.
And in that range, it often beats flying door to door.
Consistently. Because train stations are usually right in the city center. You skip the long trek out to the airport, you avoid the lengthy check-in and security queues. All that waiting time adds up.
Right. The plane might be faster, cruising at altitude, but the total trip time from your origin city center to your destination city center, rail often wins.
Exactly. And the impact on travel choices is huge. Look at Paris to Lyon after the TGV launched. Rail's market share jumped from about 40% to over 70%. Madrid to Seville. Rail took nearly 90% of the traffic by 2009.
Wow. But there's a limit, isn't there? Particularly in places like Japan, they talk about the 4-hour wall.
Yes, that's a really important concept. The data from Japan is clear. If the HSR journey time goes much beyond 4 hours, people start choosing planes again, overwhelmingly.
Can you give an example?
Sure. Tokyo to Osaka is about 2 hours, 20 minutes by Shinkansen. Rail gets about 85% of the travelers on that route. But Tokyo to Fukuoka, that's closer to 5 hours by train. Rail's market share plummets to just 10%.
So that 4-hour window is absolutely critical for HSR's competitiveness against air travel.
It really dictates where the investment makes the most sense. You need to keep those key city pairs within that time frame if possible.
Makes sense. And beyond just speed and time, there are other big advantages, like efficiency and environment.
Huge advantages. Per passenger, HSR uses significantly less energy than cars or planes. And because it's electric, the power source can be anything: hydro, nuclear, wind, solar. It moves the pollution away from city centers, and you can decarbonize the power source over time.
So it's potentially a much greener option long term.
Definitely. Plus, the sheer capacity. A typical double-track HSR line can move far more people per hour than a multi-lane highway, using much less land.
How much more?
Well, one figure suggests about 13% more capacity than a 6-lane highway, while using only about 40% of the land. And think about the Tokaido Shinkansen, again capable of moving something like 20,000 people per hour in each direction. Cars just can't match that throughput.
Incredible numbers. Okay, finally, we have to touch on safety, because the record, especially Japan's, is just phenomenal.
Yeah, it truly is. The Shinkansen's record is legendary. 0 passenger deaths caused by train accidents, derailments, collisions since it started in 1964. 6 decades. That's an unparalleled safety culture and system design.
It really sets the benchmark. But for balance, we should mention that major accidents, while rare, have happened on high-speed systems elsewhere.
We should, yes, to be objective. The 1998 Eschede crash in Germany was tragic, caused by a wheel failure on an ICE train. The 2013 Santiago de Compostela accident in Spain involved a driver taking a curve onto a conventional track section way too fast.
Right.
And the 2011 Wenzhou collision in China involved signaling failures on a high-speed line, though speed itself wasn't the primary cause of the initial crash. But what these awful events often highlight is just how critical that integrated system approach is. The dedicated tracks, the advanced signaling, the automatic train protection, they're all designed to mitigate human error or mechanical failure. The safety record is tied directly to that system integrity.
So wrapping this up for you, our listener, HSR isn't just about speed. It's a complex, highly engineered system defined by its dedicated infrastructure. And it absolutely dominates that crucial 1 to 4 hour travel market.
And we've seen that building this infrastructure is a massive undertaking. Very expensive. New tunnels, bridges, specialized tracks, usually justified by linking major population centers, major economic engines.
But the effects ripple out much further than just faster trips between big cities. So here's a final thought for you to chew on, something about how HSR might be subtly reshaping where and how we live.
Okay, think about a town in Germany called Montabaur. It's not huge, but it happens to have a station right on the main high-speed line between Frankfurt and Cologne.
Two major economic hubs.
Exactly. Because the HSR connection is so fast and reliable, people can live in Montabaur, where housing is cheaper than in Frankfurt or Cologne, and commute easily into those big cities for work.
Okay, that makes intuitive sense. But is there data?
There is. And it's fascinating. Montabaur apparently has the highest per capita rate of Bahncard 100 holders in the whole country.
The Bahncard 100. That's the pass that gives you unlimited travel on almost any train in Germany for a year, right? Including the high-speed ICE trains.
That's the one. So people in Montabaur are using HSR so much, so routinely for commuting, that buying this expensive, unlimited annual pass makes financial sense for them, more so than anywhere else in Germany on a per-person basis.
Wow. So HSR isn't just connecting cities, it's effectively making places like Montabaur viable, affordable commuter hubs for major employment centers hundreds of kilometers away.
It fundamentally changes the calculation of where you can live and work. It expands the labor market, potentially revitalizes smaller towns. So the question is, how much does HSR change not just travel speed, but the actual geography of our lives and economies?
Something definitely worth thinking about next time a new HSR line is proposed.
Yep.
And that is all the time we have for this deep dive. Thanks for joining us. We'll see you next time.